Yeah.
Okay.
There you go.
So our next speaker is going to present a technology that actually has been part of the TIP process and its precursor for about 2 years. Is that right, Chad?
That's right.
So
yep.
This has been in development for 2 years and will be announced as available for licensing next week. So pay close attention, and I hope you find some areas of interest here. And this is Chad Duty, and he's going to talk about nanofermentation.
Nanofermentation. All right, I'm on. I assume I'm on. They'll come out and tell me if I'm not. So yeah, thanks for coming back in from the break to talk about nanofermentation. Nanofermentation is kind of an interesting project. This is something that can really only happen in a national lab in terms of cross-disciplinary research. It's really interesting in that it was developed out of a biological sciences perspective. We have these guys that their job in life is to go around and go into deep, dark caves and behind the ropes at Yellowstone National Park and kind of find these really toxic environments and find the bugs that are living inside of them and study them. And how in the world did they survive? So they find these really toxic pools. And these bugs are surviving inside these toxic pools by precipitating out in solid form the really toxic environment that's in the solution. And then they drop it out of solution so they make their environment more habitable. So we take these bugs out of their natural environment and bring them into the lab. And there's several different varieties of the bugs. They're extremophile bacteria. And we see how we can change the solution that they're in to produce different types of nanoparticles. Because when they precipitate out that solid and drop it out, they're actually making a nanoparticle. So when we start talking about nanoparticle production, which is what we're going to talk about as part of this research, you basically take a big beer brewing vat, fill it with water, put in the bacteria, add in some sugar to keep them alive, some nitrogen to keep them alive, and then you basically try to poison them with sulfites and salts and things like that. It's really kind of bacteria torture, to be quite honest about it. You put them in an environment that they absolutely hate, and that self-defense mechanism kicks in, and they start producing these nanoparticles. Really complex, as we'll see, nanoparticles. They actually double in population every 3 hours, so it's kind of like a yeast starter for bread. You just keep the part active, and then you can control the size, shape, and composition of these particular nanoparticles, and then you just collect them for whatever use you have for these particular nanoparticles. So, as I mentioned, it's kind of like brewing beer. Instead of putting in yeast and barley and hops and things like that, instead of the yeast and barley you put in, or barley and hops, you put in salts. Instead of the yeast, you put in bacteria. And you feed it sugar just like you would for beer. Now, they produce CO2, just like in beer, but instead of producing beer, and everybody goes, they produce nanoparticles, really highly valuable nanoparticles. And by changing the soup, or the concentration of the nasty, toxic environment that they're in, we can change the composition of that nanoparticle that they produce. So we've produced magnetic nanoparticles, semiconducting nanoparticles, photovoltaic materials, and phosphor nanoparticles. And the crazy thing about this technology is right now, we don't know what we can't produce. We really don't. In terms of looking at various different materials, we're not really sure what we can't do, because there's always little games that you can play with the chemistry. And so far to this point, within reason, a lot of the things that we initially thought we couldn't do, like selenides for SIGs, for photovoltaics applications, selenium is death, literally, to bacteria. So the fact that they'll actually work with selenium is really amazing. And we've been able to get them to produce this. Now, the technology is really a platform technology. It's not just making one particular nanoparticle or another. It's really a nanoparticle production platform. You can make metal oxides for fiber optics and computer devices. You can make super paramagnetics for drug delivery and imaging. You can make ferrofluids for speakers and shock absorbers and the like. Quantum dots is really where some high value is for this type of technology in terms of photovoltaics, solid-state lighting, and displays. And there's lots of companies in all of these spaces that are currently today using nanoparticles. Now, they're not getting their nanoparticles from bacteria like what we're producing. Instead, they're actually taking a few different approaches to nanoparticle production. One is what I kind of call the caveman approach, which is the first one. Take big rock, make it smaller. So they mine these materials and then basically crush them up into small nanoparticles. Well, with that comes a lot of energy that's required, as well as a lot of waste. And a lot of that wastewater is really toxic. So it's a highly environmentally impactful technology as well as very expensive and energy intensive. The other options are chemical synthesis. That's really not very scalable. If you want to make kilograms of this material, it's really hard to make that scalable. And then the other one is to kind of skim out or filter dilute solutions. And again, that's really low yield and really poor quality. So what you get is when you start trying to use nanoparticles, you get really expensive nanoparticles. And there's a few people right now that are selling nanoparticles. Ocean, Nanotech Ocean, American Elements, Evident, and those guys. If you take even some very simple nanoparticles like cadselenide, quantum dots, you're paying about $10,000 a gram for these type of materials. If you look at a core shell type of a structure, cadselenide and zinc sulfide, you're looking at $12,000 a gram for these materials. They're very, very expensive. And keep in mind, these are just the binaries. These are not quaternary or tertiary compounds like what we're making. So the technology that we have with nanofermentation is you get these bacteria to do the work for you. And bacteria are, you're really good at making things, and this is for people too, that are about an order of magnitude bigger or smaller than you. Well, you get these bacteria to start doing the nanoparticle work for you, and things get really easy. So we can actually scale this very quickly. You can make, if you have about a 50,000 gallon fermenter, you can make about 500 kilograms of material every month. It's about 5 to 10 grams per liter per month in terms of your yield. And it's a batch type process. So just like Coors Brewery, if you have several different batches going at once, you can actually start producing kilograms and kilograms of this type of material. It's energy efficient. Basically, you need a hot water bath in order to get this to work. So it doesn't really require that much in terms of facilities or technology or energy input. It's environmentally friendly. It's kind of a green technology because these bugs are naturally doing this today in their environment. And it's low cost. So instead of the $10,000 or $12,000 or $30,000 per gram, we're actually making this material at about $1 to $10 per gram. So even if we mark it up 100% or 1,000%, we're still an order of magnitude or two below what's the current commercial value. If we start looking at where the technology is today, in terms of nanofermentation, as I mentioned, we've made several different compositions of this material. So we've made ferrites and SIGs and CZTS and cad sulfide. We've shown that we can control the size, shape, and composition. If you're not familiar with XRD diagrams, this is basically showing that we can alter the type of soup or toxic environment that they're in and change the composition of those molecules or those elements in the stoichiometric composition. So for SIGs, for example, indium and gallium, the Ig and the SIGs, that ratio really determines the band gap, which is the useful part of the semiconducting material. We can adjust that just as you would expect for this type of technique. It's relatively clean. It's not, typically when you think of biological processes, a lot of the process happens internal to the cell. This is different. This actually occurs extracellular. So all of the product that you're interested in naturally dissociates. It drops down out of solution, so it self-separates. So you can get all the good stuff and get rid of all the bacteria, or reuse the bacteria, by the way. This is a living creature, so sure, you're kind of torturing them, trying to kill them off, but enough of them live to refill the next vat when you're ready to go on to the next process. We can also scale this. This is one of the crazy things about this technology is we've gone from test tube up to, I think we're up to 24-liter vats right now. We're going to a 100-liter vat this month, and then next year, early next year, we're going up to 800 liters. And every time that we've increased the scale, we've increased our efficiency and increased our yield. That's completely backwards for most biological processes. That's because we're kind of, as I mentioned, we're kind of torturing these bugs. So when you put an eyedropper of material into a test tube, it's like a nuclear bomb going off, and it kills a lot of them. If you carefully seed that into a larger vessel that has a injection process, you can more carefully inject that, so you have a much more efficient process. The types of materials we made are magnetic oxides. You can basically fill in that blank with any of those materials above and look at those different oxides that we've developed. This has been published widely, and we've also won an R&D 100 award for it. There's also photovoltaic materials, and this just gives you an example of scaling up to over 1,000 times. In terms of, and the yield increases along each way, and cad sulfide and zinc sulfide. And there's several different sulfides that we could do with this process. We've also done photovoltaic absorbers. So these emitter and absorber layers are what makes up your solar cell. Some of the solar cells that you may have heard of in the press are SIGs and CZTS. The SIGs is the higher performing, more common earth, rare earth and toxic materials. The CZTS, copper tints, zinc sulfide are the earth abundant and non-toxic version of those. So we can make both of those, we found. We can also make zero valence elements in terms of catalysts that could be used for this. In terms of nanoparticles, having a large surface area to volume ratio is really useful for catalysts. And we've also shown that we can make like phosphor type materials to change the phosphor coating in your fluorescent lighting. So there's all kinds of application areas that you can go into with this. We've done a lot of work recently on ink development, as well as when you make nanoparticles, they really like to agglomerate and stick together. So we've been doing a lot of surface chemistry to be able to break those up so that you can get the quantum dot size effects that you want out of that particular material. So we've been doing a lot of work with surface chemistry and dispersions and that sort of thing. Also depositing them down in a uniform method in terms of large area coverage, and looking at surface chemistry and how they interact with the various different substrates. As I mentioned, we're scaling it up. We've got an 800-liter fermenter coming in early next year, and our production rates right now are about 5 to 10 grams per liter per month. So if you've got a 50,000-gallon fermenter, as I mentioned earlier, you're producing 500 kilograms, and if you charge a few $1,000s per gram to even stay under the competition, it's not hard to do that math. It gets pretty lucrative pretty quick. As Mike mentioned, this technology is being released. It's open for licensing. So there's a few patents. There's actually one on here that I haven't listed, but there's a few patents that are actually current, and there's several patent applications that are going to be coming through in the next few months. So this technology is going to be open for license, I think, in the next week or so, and we'll kind of send out some notices on that as it becomes available. This is the whole process from digging the bugs out of the ground, having them produce nanoparticles, all the way to scaling up and then depositing to make a thin film system out of it. That's just kind of a summary that I was going to leave up as I open up for questions. And that's it. Yeah.
Have you done any work on the bugs changing if they get older?
Yeah, genetically mutating. Okay, so that sounds bad, but it's actually could be a good thing, because what they'll typically mutate into, and by the way, we haven't genetically altered these bugs, so don't worry about that. But so these are natural bugs, but as they mutate, they're likely to get more resistant to the particular toxin that we tried to dose them with. So they'll actually likely increase their yields, because we'll be able to push the bugs harder and be able to increase the concentration in that particular environment. So we do anticipate over several hundred generations of those bugs, we do anticipate some resilience to build up, but that will likely make the process better. We really haven't. We haven't gone through enough, we don't believe, enough iterations of that process with the same bug strain, because we've been doing a lot of R&D level benchtop tests, so we haven't really gone through the volume and the cycles that you would probably need to really see that show up outside of any sort of scatter that we already have. So, yeah.
So if you're saying you haven't genetically modified them, those bacteria are culturable. You all just kind of get lucky, so to speak?
Aren't culturable in terms of getting them to repopulate and continue. Yeah, these, if you feed them and give them a good environment, they will double their population every 3 hours. And we've actually seen that to be the case with several different strains of the bacteria. The crazy thing about this is not every bacteria strain is useful for every single material we want to make. For example, we're trying to do some experiments with a telluride, and turns out none of the bugs were resistant to the tellurium. And there happens to be a place in Colorado called Telluride, Colorado, that they mine a lot of the telluride compounds. You go out there, look for bugs, they happen to have mutated to be resilient to telluride. So you can use those bugs for that particular compound. So that's what I mean when I say we don't even know what we can't do yet. There is a certain pH-EH window that we usually need to fit through, but we found a lot of innovative ways to bend that to our will to this point. I'm sure there are some limits, but we don't really know where they are yet. So, yeah.
Does it matter if you grow these in light, dark?
They don't care. As a matter of fact, we typically, it's not shown up here, but we typically surround them with blankets. Those are more for thermal insulation than anything, but they don't care if you're in the sun or not. I don't know, quite honestly. I'm not as familiar with that as this. I tend to think of that as a digestive type enzyme type process, but I'm not familiar with that one. Yeah?
Well, this covers a broad range of products. How are you planning on doing the licensing? The platform or for specific products, bacteria? Or?
Yep. That's where Mike and Jennifer earn their money. So in terms of particular fields of use, particular processes, I mean, you named it. All those different variations on that. I don't know if you guys would like to comment on that more fully.
Well, the intellectual property is on the process, so it's the method of making the nanoparticles. And so we're going to look to see what kind of interest we have and what's the best route for commercialization. We feel we have two options. One is exclusive field of use for the various particles and uses of them. That's where you use this method. And the other would be non-exclusive in all fields of use if there's a lot of other intellectual property that's required to actually get the process to work commercially.
Okay. Yeah.
When you go on large scale commercial size, where you have 1,000 gallons of bulk,
Right.
the feedstock and the bugs, you have to go into a cave and get these. So what's the scale-up time to get it X and make that?
Right. So what you'll do is you'll probably put so we've already gone and collected a wide library of these bugs. So they're kind of sitting on the shelf and, living happily. Remember, these things are used to just living in really deep, dark holes with toxic environments. So putting them on a shelf and keeping them alive is really not a big deal. So what we do is we would culture those or give them a healthy environment in which to repopulate. And they can double their population every 3 hours, as I mentioned. And if you just have a geometric progression of them doubling, they'll very quickly get up to size. I mean, it may take a few weeks to get to the 50,000 gallon type range, but that's not. And you treat it almost like a starter for your yeast or for your sourdough bread or something like that. You kind of dip out little pieces and then grow that culture and then move forward with that. I'm not a biologist, but in the guys that I've talked to, that's not really seen as a stop point or even an issue of concern with them. I don't want to. How much more time do I have? Or I don't. Okay, so that's
Where do you get the toxic soup starter?
salts. So you just buy salts. So that's when you start talking about comparing this to typical solar cell type manufacturing processes that might occur in a big vacuum oven with physical vapor deposition or sputtering targets. You have to have really pure targets to be able to make the material. With this, you buy really cheap salts, and you buy a copper salt or a selenium salt or something like that, and they'll pick out those compounds through various different chemistry that you want them to pick out to make the particle. So it's a really cheap process. Yeah.
You mentioned before nanoparticles.
Right.
Selectivity involved with this platform.
Selectivity in terms of them choosing the right nanoparticle that we want them to make. It is a bit. So in terms of making, so they won't exclusively make like the quaternary compounds, but we can usually separate those out either chemically or centrifuge or what have you to be able to separate those out. Typically you can drive the chemistry to have the highest yield for what you want, but typically a lot of those even lower orders, the binaries and the tertiaries are also of value. So it's kind of a business case to look at the yields for particular strains or for particular compounds that you have to look at. Yeah?
How many different species of microorganisms have you sampled?
You'd have to talk to the bug guys about that. I'd say it's in the tens, if not hundreds. I'm not really sure about that. But the ones that he has seem to be fairly robust in that they'll work with a lot of different compounds. No, he's going all over. And this is the guy I really envy. You see, Tom, well, no, it's gone on to Togas, but he goes all over the world, down to Africa, all over the United States, he was in Alaska a couple months ago. It's really a tough job. Yeah. So, thanks.